Our universe is a vast and mysterious place filled with wonders that stretch beyond our imagination. Billions of galaxies sprawl across unimaginable distances, each one a unique island of stars and cosmic phenomena. Each galaxy is home to billions of stars, and many of those stars have planets orbiting them, creating potential homes for life. This cosmic tapestry is breathtaking in its scale and complexity, a grand design that leaves us in awe. But what is it all woven from? What is the underlying structure that holds this vast universe together? What is the fundamental fabric of this grand cosmic design? What threads bind the stars and galaxies in this intricate pattern? The answer, as far as we know, is the time-space continuum, a concept that merges space and time into a single entity. Imagine a giant, invisible sheet spread out in all directions, a fabric that stretches across the entire universe. This sheet isn't just a flat surface, it's a four-dimensional realm where space and time are intertwined, creating the stage for all cosmic events. This is the time-space continuum, the very essence of our universe, the framework that supports everything we see and experience. Everything that exists, from the smallest particles to the largest galaxies, resides within this cosmic fabric, interconnected in ways we are only beginning to understand. It's the stage on which the grand cosmic drama unfolds, the canvas upon which the universe paints its breathtaking masterpiece, a masterpiece that continues to evolve. Understanding the time-space continuum is key to unraveling the mysteries of the cosmos and our place within it, offering insights into the very nature of reality itself. The concept of the time-space continuum wasn't always readily accepted. It took years of debate and skepticism before it became a cornerstone of modern physics. For centuries, scientists believed that space and time were separate and absolute entities. This belief was deeply rooted in the works of early astronomers and physicists. Sir Isaac Newton, in his groundbreaking work, described a universe where time flowed uniformly and space was a fixed and unchanging grid. His laws of motion and universal gravitation were revolutionary for their time. However, in the early 20th century, a young physicist named Albert Einstein shattered these long-held beliefs with his theory of relativity. His ideas were initially met with resistance, but gradually gained acceptance. Einstein proposed that space and time were not separate entities, but were intimately connected, forming a unified fabric, the time-space continuum. This was a radical departure from Newtonian physics. This revolutionary idea had profound implications for our understanding of the universe. It changed the way we perceive the cosmos and our place within it. It meant that gravity, rather than being a mysterious force acting at a distance, was actually a curvature in the fabric of space-time caused by massive objects. This new understanding of gravity was groundbreaking. This curvature, in turn, dictated how objects moved through the cosmos. It provided a new framework for understanding the motion of planets, stars, and galaxies. One of the most mind-bending aspects of Einstein's theory of relativity is the concept of time dilation. Time, as it turns out, is not absolute, but is relative to the observer's frame of reference. Imagine two identical clocks, one stationary on Earth and the other traveling at incredibly high speeds through space. According to Einstein's theory, time would pass slightly slower for the clock in motion compared to the stationary clock on Earth. This phenomenon, known as time dilation, has been experimentally verified using atomic clocks flown on high-speed jets. While the difference in time is minuscule at everyday speeds, it becomes increasingly significant as objects approach the speed of light. To grasp the interconnectedness of space and time, imagine a bowling ball placed on a stretched rubber sheet. This simple analogy helps us visualize the complex nature of space-time. The bowling ball represents a massive object such as a star or a black hole. These celestial bodies have immense gravitational pull. The rubber sheet represents the fabric of space-time. Just like the sheet, space-time can be stretched and warped by the presence of mass and energy. The weight of the bowling ball causes the rubber sheet to sag, creating a curvature around it. This dip is a visual representation of how gravity works. This curvature is analogous to the curvature of space-time caused by massive objects in the universe. The more massive the object, the greater the curvature. Now imagine rolling a marble across the rubber sheet. The marble represents a smaller object, like a planet or a spacecraft. Instead of traveling in a straight line, the marble will follow a curved path around the bowling ball due to the curvature of the sheet. This demonstrates how gravity bends the path of objects. This is similar to how the gravity of massive objects influences the trajectory of objects moving through space. The gravitational pull of stars, planets, and black holes shapes the movement of everything around them, guiding their paths through the cosmos.